Well, classes and objects all may seem a little confusing to you, but one thing to remember is when you define a class, you are defining your own data type, be that a data type of a circle, as the text has been using, or a data type such as a bank account, as we'll be looking at. So the first part of the chapter simply introduced us to classes and objects in a very simplistic manner. This final lecture and the remainder of the text will address some of the more nuanced type issues dealing with class definition and the use of objects. So once declared as a variable, you can use an object's methods to manipulate the object. That is, you can change a circle's radius, or you can compute a circle's area. And once the class is defined, all the heavy lifting regarding the validity of the instance variables or any computations required by the class have all been completed and tested. The program need only instantiate the object or objects and use its methods to accomplish a program's stated purpose. Remember, classes are not programs. Classes are used by programs to create objects and to manipulate objects of that class type. We've used classes and objects from the first weeks in here. Math.pow or math.random using the math class methods. Note, in the case of the math class, we did not create any objects of type math. We simply referred to the class dot the method we wanted to use. And when we discuss static later, this might become a little bit more clear. In addition to the math class, we've also been using the string class. And during these past weeks, we've been creating objects of type string, and we've recently learned about how to use the string methods. So as far as accessing an object's methods or its properties, we've been using the dot operator, such as string name dot substring. Let's trace through the instantiation of a circle object. The highlighted portion in this slide declares my circle to be of a data type circle. And note that the variable has no value. It is null, not 0 and not blank. It simply has no value. And that's what null represents, no value. So at this point, our program calls or invokes the circle's constructor method, telling it to create a new circle, instantiate a new circle object with the radius of 5, and which it does and places it somewhere in memory. Well, when the constructor finishes, our program variable, called a local variable, is set to the address of where this newly created circle object is in memory. Now remember, object variables are reference variables. They are not the object. We often refer to the variable as if it was the object, but be mindful it is only a reference to the object. Well, now we're in the process of instantiating another local variable of type circle. We've had programs in the past where we've had multiple integers and variables and several string type variables and double type variables. And so there's no limit to how many variables of a different class type you can have. And so we're creating a second instance of circle, and we'll name it your circle. In the case of your circle there, we've used a no argument constructor. So a circle constructed with the no-args constructor in this class, it has a radius of 1. 1 happens to be the default radius as defined in the class definition. Now, your circle has a memory address pointing to the newly created circle object, and my circle has a memory address pointing to my circle object. My circle does not equal your circle. Why? Because the reference addresses are different, not because the radiuses are different. I mean, I could have created your circle with the same radius 5. If we want to compare the circle objects to see if they are equal, then we would need to develop a class method to do that comparison. Well, remember, we constructed your circle using the no-args constructor, which gave it a default radius of 1. So here, this little highlighted code sets the radius of your circle by changing it directly, accessing your circle's radius property. As we'll come to learn, hopefully, directly accessing the object's properties can be dangerous business. What if the programmer inadvertently set the radius to -100? Directly accessing the property would allow this. Well, we've seen 2 ways for referencing methods. The first is to use the class name .method name, such as math.pow. And the second is to use the object variables name .method name, such as myString.substring. Well, all methods used before this chapter have been defined as static methods, using the static keyword. As we'll come to learn, static properties and methods are very special and are not commonly used in class definitions. We'll be using them simply to demonstrate for demonstration purposes later. However, as a general rule, an object's properties and methods are non-static, and they must be invoked using the object variable name .method name notation. Well, this slide is meant to call attention to class variables and properties. Unlike our local or program variables, which require that we explicitly initialize them, class variables take on default values if not explicitly initialized. So there's no restriction regarding the data types that we can use in a class. We can use the primitive types that we've come to learn, as well as using other object types in our class. In the student class above, the name is a string object. It's a reference data type. And if a reference data type does not have a reference to any object, the data field holds a special value called null. Null is a reserved word, and it simply means it has no value. It doesn't mean blank. It doesn't mean 0. It simply means there is no value. The value is indeterminate. So null is a reserved word similar to true or false. Now this little demonstration class above has 2 methods. It's constructors, and remember, a constructor is always uses the name of the class, and it never has a return type, not even void. And the second method is what I had referred to in an earlier lecture as a getter. Nothing special about it. We simply name it get for convention reasons. Now pay special attention here. Classes do not have a main method. Main methods only appear in programs. Classes are not programs. classes are not executable. Classes must be used, or sometimes you hear the word consumed by a program. For demonstration purposes, I threw together this little tester and student class. Whenever you develop or create or define a class, you need to write a little tester that will exercise the class's methods and validate that the class is performing as you have intended. Now, this class is in no way a proper definition. I would not recommend this as being the way to define a class. Notice our class has no constructor. So we'll simply let the Java runtime environment implicitly build a no args constructor. Now, the demonstration is in the tester program to display the returned value of the test name method. Note, in the student class, name is not initialized, so its value is null, and the test name method will return true. Furthermore, you would not get away with not initializing a variable in tester. Programs don't like not initializing variables. I think you should note also that student as a class is not defined as part of tester. Notice that it is outside of the brackets that enclose the tester class. So student class is something separate from tester. The student class is only defined in this way for testing purposes. Normally would define a class by itself without the tester. Well, here's an example of a program, and I know it's a program because it has a main method, and it is choking on two variables, x and y, when I try to use them in the system.out commands, simply because they're not initialized. This causes a compiler error. The point is that in a class, we don't have to initialize our variables. They take on some default values for initialization. We've discussed primitive variables and reference variables in the past. Generally speaking, primitive variable space is allocated as part of the program data space at compile time. Consequently, the memory address of a primitive variable is known at execution time, whereas reference variables need space to be allocated dynamically from available memory at runtime, and the address of a reference variable cannot be determined until it is created, instantiated, using the new operator. Well, we've learned before that copying primitive variables or copying reference variables have different results. When we copy one primitive variable to another, we have two variables occupying different memory locations, as in copying I to J. But however, when setting one reference variable equal to another, then both the reference variables end up pointing to the same object. So note that when we say C1 equals C2, C1 and C2 point to the same object. There is no longer a pointer to the C1 object. It's an orphan. Garbage. Garbage is automatically collected by the Java virtual machine, which frees up the memory that was occupied by C1. This process is known as garbage collection. So garbage collection is cleaning up that memory space that is no longer referenced. Now, if you know that an object is no longer needed by your program, you can set its reference value equal to null. Remember, null is a key word, so we could simply say C1 equals null. And the Java virtual machine then would clean it up the next time it goes through its garbage collection routine. Well, this slide gives a UML diagram for the date class. It's part of the Java util package. Now, a package can be thought of as a section of a library, just as fiction books in a library are stored in one location, different from nonfiction books. Now, the util package stores classes of utility nature, and the I/O package stores classes dealing with input and output of files. Well, you can use the date class to create an instance, instantiate an instance for the current date and time by using the noargs or empty constructor of the date class. And then we can use its toString method to return the date and time as a string. Much simpler than that date program that we exercised very earlier in the semester. Well, we've used math.random, the math class, to obtain a random double value between 0 and 1, excluding 1. But a more useful random number generator is provided by the util package and the class random. Well, simply look at how easy it is to generate a random integer less than 100. We've kind of jumped through hoops before by generating a random number and multiplying it and then casting it. Using the random class, it's fairly simple. Well, note that in this example, though, of using the random class, I had to create an object of type random using my random equal new random. And I would have had to import the java.util.random class in order to do this. If two random objects have the same seed, they will generate identical sequence of numbers. For example, the following code creates two random objects with the same seed 3. You may not want to set seed in practice during production because you want a truly random sequence of numbers. Using a seed, you get a predictable sequence. Okay? With random number generators, if you want a predictable sequence, then you set the seed. I.e., it's kind of like a beginning value. If you use the empty constructor, Java will use the system clock as a seed. Its value will always be different. Consequently, every time you run, it will produce a different series of numbers. But for program testing purposes, using a predictable seed, you can predict or use or understand the values being generated so that you can understand the output results. Well, we've been referring to creating new objects as instantiation. Technically, an object after it's instantiated is referred to as an instance. And instant variables belong to that specific instance we might have instantiated. So when we instantiate myCircle, we create an instance of a circle class named myCircle, and the variable radius that belongs to that instance has a specific value. Now, our second instance in this program snippet, yourCircle, is another instance of the circle class, and it has an instant variable that belongs to it. So myCircle has a radius of 5, and yourCircle has a radius of 100. Now, just as instances, objects created from our student class, each student has a unique instance variable name. So no two instances share the same name, just as no two instances of the circle share the same radius. Methods also belong to the instance. That is why in the slide, toSystem.out statements report different areas. They are computed in the same way, but I can't ask myCircle to compute the area of your circle. Static variables are shared by all instances of the class. In this example, count does not belong to any one instance of the class student. It is being used to keep a count of the number of student instances created. So the keyword static makes a variable or a method, more correctly, a class variable or a class method. So recall that the math class, we referred to its method using its class name. So static methods and or variables are not unique to a specific instance. And constants that a class may use are always static. They're always the same for all instances, and are final variables shared by all the instances of the class. This little example of instantiating two student objects would increase count by 1 each time I created a new student, and consequently the static variable or class variable count now would equal 2. But note in the UML notation of our circle UML diagram that any shared, or as we've known it, static methods or variables have their names underlined. Reference to these static methods or shared methods is by using the class name dot method name. In the example, the constructors set the value of radius and add 1 to the number of objects. The graphic is trying to show the number of objects is shared by all instances as a class variable, and radius is unique to each instance object. So in the example, if we wanted to report the number of circle objects we created, we'd use circle dot get number of objects. Notice we use the class name, right? We use the class name to access static or shared methods and or variables. Well, here we've defined our circle class. We've added a static or slash shared variable, number of objects, and a shared, or as we might call it, a static method, get number of objects. So when might we use static variables or static methods beyond simply keeping the count? Well, suppose in the bank account class, we want a total or an average of the balances across all bank accounts. Then we might take total, and it doesn't belong to any one instance, and neither does count, for example. And so we might make the number of accounts and the total balance static variables. Not only can we accumulate the total of our account balances, but we'll also be able to compute the average of the account balances across all accounts. Now, I've been waiting to get to this point. That is the use of the accessor modifiers to limit the visibility of properties and methods. By limiting visibility, I mean what is exposed to the programmer for use. In practice, and that's best practice, class variables should never be directly exposed. If they are, there's a good chance that they will be misused or corrupted. So we're encouraged to use the private accessor. Data or methods that are private can only be accessed within the declaring class. Get and set methods are used. They're exposed to the using program, so the using program can read and or modify the private properties. The public accessor exposes the class data or methods to any package or a using program. In the examples on the slide, in package 1, P1, we have two classes defined, and class 2 instantiates an instance of class 1, but it has no access to variable Z or method M3 because they are declared as private and can only be seen inside of C1. Now, package 2, class 3, also instantiates a class 1 object, but because it's not part of the package 1, it cannot see or use Y or M2 since they are not explicitly declared as public. They are implicitly declared, but not explicitly. They are public as far as the package 1 is concerned, and all classes in package 1 have access to them. In the bottom example of the slide, package 2 can't even see class 1. That's because it's implicitly declared public, but only to the package in which it resides as a public. It is best to use the public and the private accessor modifiers in order to explicitly control the access to your class variables and methods. Don't take the fool's way out and simply make everything private. If you did, the class would be unusual. Also, making everything public is dangerous business as well, in that you can easily lose control of the integrity of the class object. So be very, very, very mindful of what you want to expose public and what you want to keep under control of the class private. Now, panel A shows that a class can access its own private variables and methods, but as panel B shows, outside of the class, even though we have instantiated a foo object, we cannot access private variables and methods. So why private? Business rules can be implemented in the setters. We'll take a look at a small snippet of code next, but the class author only needs to notify users of the class, the programmers, of changes to signatures of public methods and the new public methods that might have been added. So it makes the class easier to maintain. Private makes the class variables data easier to protect. This UML diagram indicates the student class has two private variables. The minus sign in front of our private variable names, or if I had private methods, there would be a minus sign in front of their name. The plus sign indicates that they are public. There are three constructors, one with no args, and two that take arguments. And there are a couple of setters which take arguments. I simply used different names for the parameters to emphasize names aren't important. Neither setter or returns any values. There's also a getter in the UML design. So now let's take a look at the implementation of the student class. Now this class implementation is nowhere a complete implementation of a student class. There would be many more properties and methods. The thing I want you to pay attention to is the two parameterized constructors. Note how they are using the class's setter methods. This is especially important if there are business rules we want our class to implement, such as a student's name should be all uppercase, or the GPA must be greater than or equal to 0 and less than or equal to 4. So we see our two setters implement these business rules, and by having the constructors use the setters, the code for the business rules only need to be written and tested once. Now, don't worry about that throws exception code. You'll learn about this in CSCI 295. There's nothing special about the getter implementation. It simply returns its required value. Well, data field encapsulation simply means that the class contains everything to modify and or retrieve our data variables. We want to protect and hide our properties from direct access by the programmer. We want the programmer to use the class's public methods to access the properties. Now, the circle class, as described by the UML diagram, has two properties. One is an instance variable, radius. So every instance of circle will have a radius. And the other variable, number of objects, is a class level variable. So all instances of the circle will share the number of objects variable. There's also a class level method, get number of objects. Now we know that these are class level because they are underlined, and during our implementation of the circle class, number of objects and get number of objects would have the static keyword added to their declaration. So remember that instance variables and instance methods are referred to by using object variable name dot instance variable or dot instant method name. And static variables or static methods are referred to by a class name dot variable or method name. You know, I think I should have pointed out much earlier that constructors can only be invoked during the instantiation of an object. That is, in conjunction with the new keyword. So once we create our objects that we need, we don't use the constructor methods at all. To the left of this little visual aid, it shows how a primitive variable has its space reserved for it during compile time. And primitive variables occupy part of the program's memory space, whereas reference variables have their memory allocated at one runtime. And so to reinforce the difference in passing variables, primitive variables are passed by value. That is, a copy is made of the variable and sent to a method. And any changes a method may make to that variable are never reflected back in the calling program. Now with objects or any other reference type variable, the object's reference is passed. The receiving method has access then to all of the object's public methods and variables, and any changes that might take place under the control of the method are reflected back in the calling program. We've seen this when we were working with arrays, and we passed an array as a reference variable to one of our methods. Well, we've used arrays to store integers and other primitive variables. We can likewise create arrays to hold objects. Nothing special in doing so. The same code that we use to create a primitive array can also be used in a similar manner to create an array that holds objects. Above, we have code that creates a 10-element array to hold circle objects. Now, I misspoke a little bit because I said my array of circles. What the array actually holds are the reference variables of the circle instances that had been created. The array doesn't hold the circles. It holds the references to the circles. So when we invoke, for example, using the first element, circleArray bracket 1 bracket dot get area, as in the system out statement, there's two levels of referencing going on here. As shown in the figure, first of all, the variable circleArray references the entire array. And then circleArray bracket 1 bracket references that one particular circle object. And we see bracket 1 references a different circle object and so forth. Well, we've come to the end. Not only the end of this lesson, but the end of the semester. It's been a great semester from my point of view, and I hope you've learned a lot and have not been too frustrated by some of the programs I've thrown at you. In a week or so, you'll be able to relax. You'll have that one last programming surprise I have in store for you turned in, and finals will be over, and you really will be able to relax. I'll miss you. It's been a fun class.